I was looking at
There's nothing good about online.
Yeah, I'm really sad about that.
When you get like the shops, they're like €11.
That's worth it, probably.
I imagine they probably have some year before.
Yeah, I haven't asked them yet.
Okay.
Say a few words about this. Just give me a signal when I can start.
It's 6 hours and 45 minutes. It's very specific.
Hi, I'm Nicosia. I'm Joel.
All right. We apparently have a hard cutoff for lunch, so I think I will go ahead and start. And by way of introduction, let me just say that I was a student at a school like this, but it was about 15 years ago, give or take, and time flies. Unfortunately, it doesn't seem like it's been 15 years. But so I'm just going to use the blackboard today. Eventually, we will reach the limits of my ability to draw things or write complicated equations, and in later lectures, I'll use some slides. Here, more than the other lectures, this is going to have a bit of mathematics, but it's very much from a physics point of view. Math intro just means, since this is a school on topology, I want to define a couple of the standard types of topology to give you some background for what these topological quantities really mean. But it will all be by example rather than rigorous or particularly complete. And I realize that looking around the audience, I recognize a few people who will know all this already. I sort of think, yes.
It's for the recording, not for the...
For my internet fans. Good, yes. It's flashing. Now it's sometimes green and sometimes red. So I think green is good.
Should be all right.
Good. All right. But I promise we will get to some interesting physics by the end of the day. In fact, we will get to what was one of the hot topics at Les Ouches around 1978 or so, which as far as I know was the first time that topology kind of crept into condensed matter. We'll do that as sort of a warm-up, and it actually has applications to the modern things we'll be talking about in all the later lectures. Okay, so what is topology? Well, the particular kind of topological quantity that I'm going to focus on for most of what I do is an integral of something, usually something with a local geometric meaning. And the reason for that, in general, there are many ways to write almost any topological invariant you can think of. And some of them are easy to calculate on a computer. Some of them are more intellectually appealing or whatever. The ones that are the most directly connected to physical observables, at least I think the way to write them is in terms of integrals of something. Because often when we go from an insulator to a metal or something like that, or maybe an insulator with low symmetry, these things are no longer topological invariant, but they still mean something if we choose to write them the right way. Like the first example is something Leonid talked about, where the same Berry curvature that in an insulator is quantized and gives you the quantum Hall effect, if you have a metal with only partly filled bands, and you only integrate over the filled part of the band, then you get something that is not quantized but still meaningful. You get this anomalous Hall contribution. Although exactly what happens with disorder is a little subtle. We might come back to that later on. So anyway, the roadmap today is mostly intro, but with a few, I hope, nice examples. I will talk about the Berry phase, but in sort of a different way. I think it's not the worst thing to hear twice from different people. I'm going to give the lazy person's derivation, so I won't go through quite the same algebra. Then integer topological phases. What I mean by this are cases like the integer Hall effect and topological insulators. These are basically topological phases that I can understand without needing interactions. We believe that they're stable interactions. They can still be defined, but they're different from something like the fractional quantum Hall effect, which fundamentally requires interactions. Then metals and disorder. If I want to talk about gapless systems in the physical world, I usually need to think about some level of disorder, like real metals work the way they do because of disorder. And of course, topological phases, one nice feature is that they can be pretty stable with respect to disorder. And then topological responses get into what do you measure that is physically quantized in a topological system. And in topological insulators, that's a case where the non-abelian part of the Berry phase that we haven't heard much about so far is actually part of the story. And then what I cover in the last couple of lectures is going to depend maybe on what other people cover and so on, but one thing that you should definitely learn from this school, whether or not it's from me, is a bit about the fractional quantum Hall effect and Chern-Simons theory. Okay, so the most intuitive example of topology I know is the topology of just real surfaces in three-dimensional space. And I want to say a few facts about that because actually the Berry phase and the quantities that are derived from it, you can think of them intuitively as a lot like real curvature, that is, curvature of an actual manifold. So I think this analogy is useful, and it's very quick. And it gives maybe the first nice example of a topological quantity expressed as an integral of something local. So suppose I have some three-dimensional object. Maybe it's quite complicated. And I'm going to focus on one point, let's say here, and draw the tangent plane to that point, and let's say that the normal to the tangent I define as z. Then my tangency conditions are, if I can define the surface locally in the vicinity of this point as z of xy, then dz dx, dzy, both evaluated at this origin, are 0. So that means we can expand z in terms of second derivatives, and the point of doing this is that they're going to be two radii of curvature. They could be both positive, both negative. I'm assuming that I've oriented this somehow. What's going to be invariant is actually whether the two curvatures are in the same direction or in opposite directions. But these two radii of curvature you can think of as kind of the natural coordinate system near that point. In the sense that if this is true, I might as well go ahead and expand z of xy using undergrad calculus is something like okay, so this matrix, whenever we see a symmetric matrix in physics, it's symmetric because partial derivatives commute. We would like to diagonalize it. When we do so, well, that's just picking a coordinate system for the tangent plane, circle on the origin, where let's say that theta runs this way, so x is r sine theta, and y is r times 1 minus cos theta. Then, following this same expansion process, I'll get that near this point, y is like x squared over 2r. You can see it's quadratic, and there has to be a 1 over r in order to get from r squared back to r, and the 1/2 is just coming from when I expand the cosine up to quadratic order. There's a theta squared over 2. Okay, so that's this 1/2 here is the only minor thing I need to keep track of when I interpret these eigenvalues as radii of curvature. So the magic statement is the following. I could make maybe 2 natural combinations of these radii of curvature. So the matrix in here, so I'm going to put this 1/2 in front. This matrix is called the Hessian matrix. To be precise, from over here we see that once I pull out that factor of 1/2 I put in front, the eigenvalue, the coefficient of x squared, is 1 over the radius of curvature. Or in other words, our determinant of the Hessian matrix is the so-called Gaussian curvature. So if this matrix is called H for the Hessian, then determinant of H, that's lambda 1, lambda 2, the product of eigenvalues, which I can think of as 1 over the product of the radii of curvature. There's another notion of curvature, mean curvature, which we're not going to need because it's not as topological. Okay, so if we take the Gaussian curvature, here's our first example of a topological invariant. And as I said, I'm not going to prove things, I'm going to do examples. Let's try integrating the Gaussian curvature over an area of a closed surface in 3D. So I want to integrate that H dA, or integral lambda 1, lambda 2 dA. So the first case, to make it simple, suppose that this object I drew was a sphere. Then, okay, this is 1 over r for a sphere. This is also 1 over r. So this thing is 1 over r squared. The area is 4 pi r squared. So for the sphere, the integral of the curvature is 1 over r squared times 4 pi r squared, or just 4 pi. And the magic is that if I distort the sphere into this thing I drew here, which is not a sphere but is continuously deformable to a sphere, then I will actually get the same answer. But I don't always get that answer. So it would be interesting if every time I integrated the curvature I got 4 pi. turns out that every time we integrate the curvature for something that's topologically, in other words, smoothly deformable to the surface of a sphere, we get 4 pi. But a simple example of something that doesn't give 4 pi, let's take this circle and rotate it through the third direction around the line. So if this was y equal to 0, let's rotate around the line y equal to -1, say. So this will come back through as another circle down here. If I wanted to draw the whole thing, I would draw it, I guess, like this. So this is my donut viewed side on. And let's calculate the total curvature of the donut. Well, at every point, there are 2 radii of curvature again, and one of them is around the small circle, so that's easy. That will be a radius of curvature r, or an eigenvalue 1 over r. The second one actually depends on theta. And in particular, the torus is different from the sphere in that the torus has some points with positive curvature, which means that these two have the same sign. And note that whether this is positive or negative doesn't depend on how I oriented the surface with respect to the tangent plane. So I could get positive or negative there. In the sphere, the curvature is everywhere positive. Here, let's say at this point, both radii of curvature have the same sense, while here, one of them is curving outward, and one of them is curving, well, one of them is curving in that sense, and one of them is curving in this sense because it's kind of going around like that, and that is a point of negative curvature. If you work out what is the second radius of curvature of this object, and remember this condition that they're in orthogonal directions and do the geometry right, you'll get that lambda 2 is minus cos theta over 2 minus cos theta, if I did that right. And a simple integral will tell you that if you integrate the Gaussian curvature in this case, which is a torus, you'll get 0. And again, everything you get that is smoothly deformable to a torus will give you 0. In other words, the small regions of large negative curvature, the way I've parameterized the torus, cancel out the large regions of small positive curvature. And this is related to the fact that you can write a torus just as a square on the plane, say, with periodic boundary conditions. You can make it completely flat, which you can't do with the sphere. So the general statement, Gauss-Bonnet theorem, is that if you integrate the Gaussian curvature over a, well, let's start with closed two manifolds, then integral of lambda 1, lambda 2 dA is a magic number, 2 pi times the so-called Euler characteristic, which I'll come back to next time, or 2 pi times 2 minus 2g, where g is an integer, the genus that we think of. So chi is called Euler characteristic and g is called genus. G is what we think of as counting the number of holes in the manifold, where a sphere has no holes and a torus has one hole. The Euler characteristic is arguably more fundamental, and I might mention that a bit later when we define intuitively what cohomology is. So that's our first example of curvature, which is a nice, meaningful local quantity. When you integrate it, it becomes even more interesting and becomes something topological. So, yes.
What do you mean you cut that in the sphere?
Well, then you'll have a singularity at the edge. I mean, it won't be, you can't smoothly flatten this. So you mean just squash it is your idea? The boundary, I mean, then you're covering the plane twice. It's not like covering the plane once. So, to be precise, a surface with non-zero Gaussian curvature, and There's a different notion of flatten, but I guess the right way to put it is if I try to continuously map the sphere to a planar surface, I can't do it with one covering, and there will be singularities. So maybe a more intuitive way to see that is without doing these integrals, but with homotopy, which we'll talk about as one of our forms of topology. So the two, just jumping ahead of it, the two main notions of topology we're going to define are something called homotopy, which is a notion of winding number. So you've heard winding number. This is just the formalization of that. And the second is related to, or more closely related to what we did here, which is cohomology, which is basically integrals that are surprisingly independent of small perturbations. Okay, so the reason for maybe focusing on this as an example is a bit more than just, well, we integrated something and we got something quantized. If you ask in slightly more mathematical language, what have we done here? What is curvature? Well, curvature of a manifold, the way that shows up in a process of moving something along a manifold is what's called parallel transport. And maybe the most famous example of that is, suppose you take a sphere, and maybe for simplicity, let's say you're sailing along the sphere. This is your sailboat. And you've got a gyroscope that is attached to kind of keep rotating in the plane that you're traveling in. So on a sphere, the equivalent of straight lines on the plane are geodesics or great circles. So in other words, through any point here, there is a family of great circles that I could go around, and the simplest great circle that I've already drawn is the equator. So if I start with this pointing, let's say, ahead of me, and I go around the equator, well, as I go around the equator, I'm always, it seems like, going straight ahead. But that's not true if I took a line of latitude, like up here, for example. So to stay on a line of latitude, because it's not a geodesic, I have to keep turning. So for example, if I were to keep going along this line, in order to keep from going down there, I need to constantly turn right, which means that the gyroscope is preserving its direction. It appears to be twisting left. So maybe an even more fundamental object than the curvature is what's called parallel transport, which is how do I map a tangent vector at one point of the manifold to a tangent vector at another point of the manifold, using this idea that along a geodesic, tangent vectors are preserved, or parallel transport, in a sense, keeps the direction the same, while for non-geodesic curves it doesn't. So, in a sense, parallel transport is how do I compare tangent vectors at different points? The reason for stressing that is all a gauge field is. So gauge fields don't exactly have to do with the geometry of how things are in space, but gauge field, it gives us a way to compare things at different points in space, a way to take derivatives. So to be precise, it's a way to compare elements of the Hilbert space at different points. So when we talk about a Berry curvature or Berry connection, in a sense, what we're doing is working out for a manifold where there is a bundle structure, which means it's a vector bundle, a vector space attached at every point. Instead of that vector space being the space of tangent vectors, for us it's going to be some bunch of wave functions, some Hilbert space. But a gauge field, or the Berry connection is going to be our gauge field. That is just a way to compare things at different points in parameter space. So I'll come back to this later once we've said a bit more about Berry phase and other things. But this is why the analogy to Riemannian manifolds is not just a formal thing. There is some meat to it. It's all about how do you move around either a tangent vector or a state in Hilbert space. Okay, so that's kind of the philosophy in the background. So let me now say, suppose we don't want to think about curvature anymore, but want to think about topology. Yes?
Can you go back to your example with the ring cycle and the other cycle? I don't really understand the difference between the two trajectories.
Well, let me put it this way. Suppose you were sailing along in your boat, and I was just trying to go straight. So I'm trying to look at the horizon and not curve at all. So if I started up here, pointing in this direction, where would I go? What trajectory would I go along? And the answer is, if you get your globe and kind of rotate it and look at where that point is, you'll find that it isn't actually, you wouldn't go along a line of latitude. Maybe the simplest way to picture that is, suppose I was right up near the North Pole. Then the North Pole, well, that's nearly flat. So a line of latitude at 89.9 degrees north is basically a circle. So I would be turning quite a lot to go around that circle. So basically, the equator is very special because it's the only line of latitude that is also a great circle. So instead, what I should think about, if I took any point like this and ask, what are the straight lines, the geodesics, I can imagine taking my globe and rotating it so I'm looking down on this. This is the North Pole, and draw all the lines that go through this as the North Pole, which will be some fan of great circles. But through every point, by rotating it, the nice thing about a sphere is it's a symmetric space, all the points are the same. I could rotate it to the North Pole and draw all my lines of longitude. So lines of longitude are all great circles. They're different from lines of latitude. And the lines of longitude through that point, once I put it at the North Pole, those are the geodesics. So the point is, what is a straight line? A straight line means that as I'm going along the surface, I don't have the sense of curving. But if I'm, let's say, I'll do an experiment like Leonid. If this is the North Pole, and I'm very close to the North Pole, and I'm asked, well, do the line of latitude where you are, I have to turn. So geodesics are the closest thing you can define to straight lines on a curved manifold. And parallel transport is how, if I have a non-geodesic curve, how do tangent vectors appear to rotate as I go along it? Yeah?
Perhaps a good way for these surfaces to look at it is the geodesics are the ones where the curvature in free space is perpendicular to the surface.
That's right. And I've fixed everything so I can't move into the third direction. That's right. So now let's make it a bit more abstract and say, instead of thinking about just a manifold and its associated curvature because it might be curving in space, I want to define two topological notions. And while your mind is fresh, relatively fresh, let's do the one that's maybe a tiny bit less intuitive, which is a fancy name. And the second, which is more intuitive, but actually harder from a mathematical point of view to compute things, is homotopy. So cohomology, if you're asked what are the Chern forms and things like that are the topological invariants we construct, they're related to this mathematical idea of cohomology, which in physics terms, I would say, is integrals along a path or surface or whatever that are almost, or that are locally not necessarily globally path independent. So let's start off by taking a space that for our purposes is topologically trivial and define something, and then see how it changes if I take a space that's a little more interesting. So let's start off with the plane. What I want to think about is I'm going to think about, well, to be precise, one forms, but what a one form means is something that I can use to integrate along paths. So let's say I've got a path from A to B. A and B might be the same. And I want something that takes that path and gives me back a real number. So to be precise, what I'm going to think about are cases where I integrate from A to B, and the form of my integral is constrained to just depend on what the path is doing, not on any fancy derivatives or anything. So if I took, so I'm going to work in coordinates to make everything nice and explicit and think about a vector field. So I've got two real functions of x and y. Let's call them p and q. So this f is how I'm going to define my one form, my way to compute integrals, in such a way that if you give me a curve u of t, v of t, that at t equal to 0 gives me a, and at t equal to 1, let's say, gives me b. Okay, well, the way I define my integral is integrate from 0 to 1 dt of p xy du dt plus q of xy dv dt. So this is not a path integral in the fancy sense of letting the path fluctuate or anything like that. This is just, you gave me a path, u of t, v of t, and I did this integral, and I told you this is the integral of my vector field along your path. And as we all know, in the plane, there are three statements that are equivalent, and this is kind of standard calculus, so I won't prove this, but I have a little proof in my lecture notes, which I hope will be online by tomorrow or so. In the plane, the following three statements are equivalent. So, let's say A. W depends only on the endpoints. In other words, it's totally independent of the path between t equal to 0 So path independence is statement A. Statement B is that W is equal to 0 for all closed paths. That is, if I came back to where I started. And C is that f is the gradient of some scalar function. So you certainly know how to get from C to A and B, and it's just a tiny bit of work to get from A or B to C. F as a gradient means that P is the derivative with respect to X of some scalar function, Q is the derivative with respect to Y of some scalar function. So where things get interesting is that on other manifolds, the story is a bit more complicated. And to see why you would be forced to think about that, even if you didn't want to, let's take a circle. So we'll get back to the plane in a second. But, yes?
Just to be sure, you integral x and y are u and v, right?
That's right. Yeah, so this is p evaluated at, I could replace this if I wanted to by u of t, v of t. Yeah, that's right. Same here. Okay, so suppose I asked you to take the circle and think about the following question. Let me motivate it by ideas of winding number. So let's say I've got theta at t equal to 0. And let's say this is the North Pole. At t equal to 1 is also the North Pole. Of course, there will be a subtlety, which is that theta is only periodically defined. Let's see how that shows up. Okay, so there's one case which is easy. So I'm going to think about theta of t as t goes from 0 to 1. And let's think about a couple of possibilities. So one is that, well, this kind of wanders around for a bit. So let's say it traces out a path, but where it gets back to, it is the North Pole, but not only is it the North Pole, but in this case, things look very simple. Let's call that a trivial path. If I integrate dt theta dt, I'll just get 0. Well, at first glance, if you don't think about it carefully, you'd think that's always true. But of course, I could imagine a different path which does the following. Theta, let's say, increases continuously with t. And by the time I come around, I have come back to what's the same point on the sphere. But what I've realized is that theta may not be the same at t equal to 1 if I define it as, well, I can ask at every point in time how much is theta changing. That's a nice, well-defined local quantity. But we know that this integral could actually come out to be 2 pi n. If I went around the other way, I'd get minus 2 pi, say. So that's a bit strange. It's a clue that, and let me explain this in terms of paths in the plane in a second. But what this means is that on the circle, or in the case we're going to do precisely, in the punctured plane, which is the plane where I don't require that my vector field be well defined at the origin, maybe there are integrals that are locally path independent. In other words, they're path independent under small changes. If I compute this winding number, which I haven't defined very formally yet, but we will, if I were to take this trivial path, say, and make it a little bit longer, or if I were to make it snake a bit, any little change like that is not changing this integral at all. So it is, in a sense, invariant under small changes, but there are other paths that are not smoothly connected. They're homotopically different. So this winding number is an example of something that you could compute either from homotopy or cohomology. This very different path, which is not continuously connected, will give me some other value. But again, that other value is also topologically robust. Like if I did this, I'd get still 2 pi. As long as I don't cut this, I will get, however I distort it, as long as I don't cut the path, I will get the same answer. So this is a sign that there should be something topological here. And the fact that we can write it in terms of sort of sloppy integrals, if we're not very careful about whether theta is a well-defined function, is a clue that maybe we should think more carefully about whether these three rules, how that picture is kind of modified on other manifolds. So, to make that more explicit, let's take a vector field on the plane minus the origin. Let's take R2 minus so-called punctured plane. Then, on that plane, I can define a vector field. I can define a one form. And just to explain notation, one form is something that you use to define a function on paths. Two form will give you a linear function on surfaces, etc. So A, the vector potential, is a one form, and F, the field strength, is a two form. If we consider this one, so this is my P comma Q, is or minus y dx plus x dy over x squared plus y squared. Well, why did I choose that? I wanted to make it look like this. This is just locally gradient of tan inverse of y over x. So this is like theta, but we know that similarly arctan is only defined up to additions of 2 pi times an integer. So how does that show up? Well, the precise statement is there's a difference on a general manifold between a closed one form and an exact one form. And that difference is the cohomology of the manifold, or the first cohomology group. So let me explain those terms. Exact means that the one form is a gradient, basically, a differential of a zero form. So this thing is locally a gradient, but not globally, because this is not a globally defined function. If I chose theta equal to 0 to mean the North Pole, but then I went around this loop, I'd come back to 2 pi, so that's a problem. Closed means the, to be precise, differential form is 0. And that is what shows up when I try to calculate how do things change under a local change of path. So, for example, if I were to think about computing the integral of this one form along some path from A to B, then if I make a little change here, if you want to think of it, I'm not going to formally define the exterior derivative, but the difference here will be related to essentially what was the curl of my vector field. And this vector field has 0 curl. That follows from its being a local gradient. So for our intuitive example, this is equivalent to saying 0 curl. The point is that every function, every one form that is a gradient has zero curl, but it isn't true in the other direction. It's only true for things like the plane that are topologically trivial. In general, there are one forms, and what I wrote down there is an example where there is local path independence. The curl is zero, but they are not globally the derivative of anything, the gradient of anything. So they're not exact. And that lets you define a quotient of two vector spaces, which is the first cohomology group. So one form a vector space, and that I can add them with, let's say, real coefficients. Exact one forms are a subspace of that vector space. Closed one forms are a slightly larger subspace of that vector space. So we define that H1 of some manifold is the quotient where Z is my notion for closed one forms, and B is my notion for exact one forms. So we're not going to use this right away, but let me tell you one neat thing related to what the Euler characteristic is, that number that appears in the Gauss-Bonnet formula. So let's say that if you were motivated enough, if I gave you a manifold, you could work out what these vector spaces are and try to do this quotient, where quotient means it's just a quotient of vector spaces where any two vectors that differ by one of these, I say, are the same element of the quotient space. So that's the first cohomology group. Yes?
Is it an extra group or a vector space?
I haven't said so far why it would be a group. If you want for now to just say that it's a vector space, that's fine. It is actually this de Rham cohomology does give groups. Okay, to be precise, a vector space is a group under addition. So all it means is the addition operator. So in this case, for example, in the case I just gave you, this will be R. It will be the real numbers, will be the first cohomology group of the punctured plane, which is a group with addition as the operator. Is that good? Okay. So, all right. So if you want motivation to learn more, like I'm going to tell you maybe one or two tricks for homotopy. I'm not going to tell you any real tricks for cohomology, but if you want to learn more, a physics book would be Nakahara, and a math book would be Fulton and Harris, if you actually like proofs. But here's two facts that you may know and why they're connected. So we defined Euler characteristic was 2 minus 2g. You may know that if you go to a manifold with boundary, this picks up an additional part related to the number of boundaries. The general definition of Euler characteristic for a manifold, so not just the two manifold, but whatever, is as the alternating sum of the dimensions of the cohomology groups, where these dimensions are known as the Betti numbers. And believe it or not, you've probably seen this before, even if you didn't necessarily know it, because at some point, I bet you learned that all the regular polygons, polyhedra, So polyhedra are not really continuous objects. These are just things like the square, the tetrahedron, the icosahedron, the octahedron, the dodecahedron, let's say the photonic solids. Those have an interesting property, which is that if you take the number of edges and the number of faces and the number of vertices, let me call those V, E, and F, then you get V minus E plus F is equal to 2. So for example, if you took the cube and figured out the number of corners minus the number of edges plus the number of faces, you will get, let's see, 8 corners, 12 edges, 6 faces gives me 2. That's related, that is actually a sort of discretization of the fact that the Euler characteristic of the sphere is 2, and these are polyhedra that topologically could be on the surface of a sphere. So in other words, the Euler characteristic that we defined in Gauss-Bonnet for the sphere is 2. And the particular reason why its vertices, which are like zero-dimensional objects, minus one-dimensional objects, plus two-dimensional objects, this alternation, which you've probably heard about, and if you haven't, you can check it for the 5 photonic solids, that's the same thing as this, actually, applied to this sort of discrete topology. So that's cohomology for now, but when we talk about integrals of things, the reason why they're kind of special, a lot of the objects we introduce, like cases where the first Chern number is non-trivial, those are cases where the first Chern form, for example, is something that is always closed, but not always exact. Yes?
Can you, just as an example, show us that the homological characteristic is 2 for a sphere?
Well, the way I sort of did it by... yeah, I don't think I can right away, sorry. I mean, the Euler characteristic I defined through the Gauss-Bonnet formula had to be 2 to give me 4 pi, but that's not very satisfactory. I mean, yeah, I'm not sure I could compute the cohomology groups that quickly. Maybe for next lecture.
So the subscript on the H, do you distinguish that from the subscript?
Oh, no, that's just being sloppy. Yeah, big.
The same object.
Same object. Yeah, well, actually, okay, that's a subtle... I think probably one of them would be homology and one of them would be cohomology, but in this case, they'll be the same.
Do they have the same dimensions in the way?
Do they have the same... I'm not sure what the conditions are for that to be true.
Is it start from...
I think so, yeah. Oh, sorry, go ahead.
I from 0 to... Start from 0?
I think it starts from... I mean, in the cases I'm thinking about, there's just one connected component, but yeah, I think it starts from 0.
Start 0, so maybe 0 have one conclusion, 2 make another conclusion, that's 2.
Okay. You mean for the sphere, for S2? Yeah, I think that's probably right, but to show, yeah, anyway, I don't want to I'd rather not answer than make a mistake and scar you forever, so. Yes. There is. I don't know a good example, but one quick comment on actually the most important flavor of topology that I'm not covering. I don't know if anyone is going to cover it in the school, but obviously it's good for you to learn things that older folks don't really know as well, or at least most of us don't. If you want, I'm going to do homotopy next. And homotopy, I'll make a comment at the end that homotopy is very much fixed dimensionality. You can go up to infinite dimensional manifolds, and the same thing is true with cohomology. But what you really want for physics is, in a sense, letting the dimension vary, like making statements that are kind of independent of dimension, because if you're studying a band structure, for example, it shouldn't matter whether you add another 20 core levels of uranium or don't. You ought to be able to make statements that are kind of independent of dimensionality, and the most powerful technique for that is K-theory. And there's a nice book by Atiyah. I mean, Atiyah is probably old-fashioned now, but that's the only book I've looked at on K-theory. So some of the very powerful results, I'll give a homotopy approach to Chern number a little bit later. But if you really want to prove that there are only some invariants that are stable in the limit of being able to change dimension, K-theory is actually much easier than homotopy. Like, homotopy gives you a lot of accidental stuff in a way. We'll kind of see that. So my one comment on infinite dimension would be that the things I'm talking about do work, at least for some infinite dimensional cases. I don't know if they always work. But if you're really interested in the infinite dimensional or variable dimensional case, K-theory would really be the way to go. Okay, so homotopy is relatively easy. It's at least easy to define, but hard to compute. What we want to think about, gosh, I'm not going as fast as I wanted, are cases where I've got some map from the product. Let me define the first homotopy group. So I want a product of the circle times 0, 1 to m, where, so if there's a mapping, so F is a mapping from the product of the circle and this interval to a manifold with the function from any point on the circle times 0 being one loop. Okay, so a map from the circle to a manifold you could think of as like you drew a loop on the manifold. So gamma 1 is one such loop. And f of y, x1 is gamma 2 of x. Then we say gamma 1 and gamma 2 are homotopic. And at a minimum, we want this f to be continuous. If we wanted to make it smooth or whatever, we would get more restricted notions of homotopy. So this is an equivalence relation and defines a group structure in the sense that if you gave me, the group structure is that if you gave me one loop and then a second, I could concatenate them by having, if I want to show that if gamma 1 is homotopic to gamma 2 and gamma 2 is homotopic to gamma 3, you can show that gamma 1 is homotopic to gamma 3. And second, there's a notion of combining paths, which is basically just sticking one of these after the other. So the equivalence classes of maps S1 to a manifold under homotopy those define pi 1 of m, the first homotopy group. And this is all very formal, so let's just give an example. Basically, pi 1 tells me about vortices in a two-dimensional system and line defects in a three-dimensional system. Let's see why. Okay, so what I want to think about before I talk about topological defects, let's just think about simple cases where pi 1 of m might be 0 and where it might not be 0. So pi 0, if you're curious, is just the number of components, number of connected components of a manifold. Pi 1 of the circle is z. That's the statement about integer winding number. So what I mean by that is I'm looking at, let's say that this is my M. So now I've got two circles to deal with. I've got the circle that I'm mapping from, and M is also a circle. So let's draw that. So this is M. And as I go around here, so I'm going around my S1, as I do that, several things could happen over here. So the identity of the homotopy group is just the constant map where all of these go to this same point on the circle, and that's not very exciting. It's more exciting if I wind around one time. So this is a little bit like, what do I mean by saying that this is in a different class from the constant map? So for example, the identity map is it would be like the n equal to 1 element of the integers, while the constant map would be like the n equal to 0 element of the integers. So the constant map is the one that is the identity from the point of view of the group action on that Z. A simple experiment to convince you that this loop is not homotopic to the point is that if you tie a loop of string around your finger and try to reduce it to a point, it's a good idea to pull it off your finger, which is cheating because you can't do that on the circle. Otherwise, you might have an accident or something. So that's sort of the experimental proof. I won't try to prove mathematically that these are different elements. In the same sense, I could wind around twice. Or I could wind around in the opposite direction. And basically, if you wanted to prove that these were different, you could even use our cohomology trick to figure out what are nice integrals to define, basically integrals of d theta, that would tell these apart. What if I took pi 1 of S2? Well, now we're in good shape. This is the statement that you can't lasso a basketball, say. If you try to put a loop around a sphere, you can always shrink the loop to a point while remaining on the sphere. So for example, if you gave me the equator, I would go to 10 degrees latitude, 20 degrees latitude, and so on until I got to the North Pole. So this is trivial, which I'll write as 0. An interesting case is that pi 2 of S2, or in general, pi n of Sn is always Z. And if you want, usually the way to convince physicists that something like this is true is just to give an explicit recipe where this is now about maps from S2 to S2. This integer is really the first thing related to this Chern number that's going to be kind of the hero of the physics story, probably starting next time. You could compute this, for example, by, if you want to sort of step-by-step way of computing it, you can do stereographic projection to get from the first sphere to the plane. Stereographic projection means start from the North Pole and draw a line through every point. So it's the plane with a point at infinity. And then if I compute something like n hat dot dxn cross dy n hat, where n hat is the image on the sphere of this point in the plane, this will give me something quantized. And it'll be a 4 pi or whatever. But that would be an explicit calculation of the S2 to S2 topological invariant. So, okay. It turns out that higher homotopy groups of spheres get to be quite complicated, and the best thing is to just look in a table. But pi 1 of S2 being 0 is not an accident. In fact, if I take Sn, all the homotopy groups up to the nth are trivial. And then a couple of useful things to know that come up a lot in physics are the following. Yeah.
What is n hat?
So that's, okay, so I want to get from the sphere to the sphere. So n hat is my final sphere, m. So I'm doing maps from S2 to S2 because I'm computing pi 2 of S2. So I went from the first sphere to the plane and then the plane to the second sphere. Yeah.
So wouldn't the Chern number actually be pi 2 of T2?
Well, that is going to come in a second. So it would actually be from T2 to, well, okay, depending on what problem I'm going to define. If you want to talk about two-dimensional non-degenerate Hamiltonians, it would be T2 to S2. It turns out that T2 to S2 is also Z. But there's a reason why we don't ever talk about torus homotopy groups, which is actually going to be comment number 2. So comment number 1. Even for spheres, this was a big problem for a while. So for example, for cohomology, there are kind of powerful approaches to give you all the results, at least for some simple cases that you could want. Maybe the most important non-trivial example that you'll run into a lot is that this is also Z. The second thing is that there's a reason why we worked with spheres, which is that in general, for maps from something other than a sphere, don't even have to be a group. So Tn means the n-dimensional torus. So T1 is equivalent to S1. T2, the 2 torus, is not equivalent to this 2 sphere. So as was said, you get lucky if you compute T2 to S2. Intuitively, part of the difference between T2 and S2 is that T2 does have non-contractible loops on it. So for example, if you computed pi 1 of T2, you would get that there are these 2 circles. So Z cross Z, I guess. If you are mapping to S2, that doesn't matter so much. That would matter a lot if you were mapping to S1. So this is also Z. But that's basically just luck, in the sense that suppose I looked at T3 to S2. And this is an old and fairly surprising result due to Pontryagin. T3 to S2 is not a group. It's labeled by let me write it this way. 3 integers, which you could think of as like Chern numbers for xy, yz, and xz planes. And then the 4th quantity is something like, in general, I think it's 2 times the greatest common denominator of the first 3 numbers. So in other words, whether the 4th element is integer or only Z2 or Z8 or whatever actually depends on what the first 3 numbers are, which is a clue that this is now a set, this isn't actually a group. So torus homotopy, which is indeed what we should care about for the Brillouin zone, can be more complicated. Shagang and I actually have a paper using this, and there are various others as well. Torus homotopy can be more complicated, so we should be careful. But at least in the cases I'm going to talk about, we usually get lucky and something like the first case happens, but that isn't always true. And then the last fact that might be useful, so higher homotopy groups can be hard. Actually, if you want an example of the non-trivial map, so this is a map from S3 to S2 that is not the identity. We actually know that map under a different name. It's the map using Pauli matrices to get from a 2-component complex vector to a 3-component real vector. So this, I don't even know that we give this a name in physics, but we learn it in undergrad quantum. Mathematicians, this is the Hopf map. Or at least it's equivalent. Okay, so, yes?
Can I ask one more question about this torus homotopy? If I have a way to find the opposite mapping, so the inverse map, couldn't I just deduce some results from the homotopy for S?
When you say inverse map, you mean from what to what? You mean from S to T or something?
From S to T.
But the problem is that map can't be topologically, that map can't really preserve everything, I guess. So for example, because these are topologically different, as a simple way to tell them apart is that this one has non-zero pi 1 and this one has 0 pi 1. I don't think you can find a one-to-one topologically preserving map, I guess would be the statement. So I don't know what map you have in mind, but if you give me an example, I'd be happy to look at it. Other? Yes?
Maybe if you could define precisely what's the relation between the homotopy group and the cohomology group?
They're in general different objects.
Yeah,
But there are some relations. So they're not... Okay, they're both topologically properties of manifolds, and the nice thing about the simple winding number case is that is important in both of them. That explains why the first cohomology group has dimension 1 as a vector space, and why the first homotopy group is Z. If you want an example of how they're related, if pi 1, I think let's see, so if pi 1 is trivial, then I think that's sufficient to show, it goes in one direction, the relationship between the first cohomology group and the first homotopy group. I probably have that written down somewhere.
The first cohomology group is the abelianization of the
first homotopy group, that's right. The first cohomology group is always abelian, while the first homotopy group, if you take the right vortex, condensate, or liquid crystal, you can make examples where pi 1 is not. So and in particular, if pi 1 is trivial, then a corollary of that is that the first cohomology group is also trivial. But in general, higher homotopy groups and higher cohomology groups, the only relation I know is between the first. There should be related information in both of them, but I don't know any general statement. So they're really, and as I said, there are other topological quantities. These are just the ones that appear most often in, I think, the things you're going to hear in this school. So at the moment, we're going to come to examples when we define our Berry forms and all that, but for now, just keep these in your mind. But I don't mean to present them as exactly the same. They're just different topological objects with some relation between them.
For instance, like you use to derive the fact that pi group as to the Z, right? The integrals of the n hat.
That's right. So, for example, Chern number is another case where, actually, this is maybe a good thing to wrap up. So I'm going to give my own derivation of Berry phase, but let me maybe talk a bit about, I'll start with that derivation next time, but let's use it. Since Leonid gave one derivation, let's assume that and give you another example, which is physical, about what the Berry phase means and how it could be topologically non-trivial. So Leonid said that if I take this is the vector of Pauli matrices for a two-dimensional system. Then so this set of Hamiltonians is labeled by the sphere that n lives on. Then the Berry phase I generate is traced out by, the Berry phase I generate as I move n around some path on the sphere is the solid angle enclosed by that path. Well, there's one thing you should have worried about in the Berry phase derivation, which is the following. And let's see why that might be a problem. We define it using a set of reference wave functions. Which when I derive it, I'm going to call psi I twiddle. So there's a difference between the wave function of a system as a function of time, psi of t. The Berry phase is obtained by the relationship between that and some reference wave function that is not a function of t, it's just a function of parameters. So I pick my reference wave functions that I use to define the Berry phase, but then I run into what seems like a little bit of a problem, which is if I were to take the path that goes around a little circle, say here, but let's say I trace it in such a way that I'd oriented things so that what I wind up integrating is almost the whole sphere, then you'll find something weird at first glance, which is that this tiny little integral, only over a little bit of length, should somehow be giving me the integral of the Berry curvature over the whole sphere. And for this example, the Berry curvature is non-zero. For the whole sphere. So that leads through this argument to meaning that I cannot continuously define one set of reference wave functions that continuously cover the whole sphere. So in other words, the non-zero topological invariant in this case the integral of the Berry flux is what people sometimes use the term obstruction. Basically, proof by contradiction that I can't have one smooth patch of wave functions over the whole sphere. So then you might worry, well, how do I know that I can define wave functions at all? Well, the answer is, in order to define the Berry curvature and things like that, you just need to be able to define wave functions locally, compute the Berry curvature, which is a gauge invariant object, as Leonid said, the curl of A. And then once I've got that, I can throw away the wave functions. But you might wonder, why should I have to use wave functions? Why should I have to pick reference wave functions at all if what I want to compute at the end of the day, the integral of the Berry flux, is gauge independent? There is a trick, at least for Berry flux, using projection operators, which I'll tell you later, but we don't have such tricks in general. Yes?
Sorry, so how does this work for the case of a spin-on half particle? Like, why can't you just do, like, the spin-off state is like all the time for anything?
You'll find that there's a singularity at either the North Pole or South Pole, I think. If you do, that is, if you try to, yeah, so you could make one of the patches as small as you want. 2 patches are enough to cover the sphere. But you can't do the entire sphere with 1 patch and have everything be nice and well-defined at every point. And if you're very clever and you move the singularity away from the North Pole and the South Pole, you'll find a singularity somewhere else. So you can experiment with your spinor bases, but that'll be true. So, okay, I think I want to maybe do, what does this all have to do with physics? What was in these Lesuche notes from 1978 or so that are all about how to compute homotopy groups? Why did people care so much? In addition to those notes, which are, I think, by Ponaru, there is a very nice RMP by David Merman on homotopy groups. And the reason why physicists care is the following. So what is a vortex? And this gets into not topologically ordered states, but sort of conventionally Landau-type ordered states. So your picture of a vortex would be something like, okay, let's say I've got an XY model. And far enough away, things move smoothly. There's maybe a core where things are not smooth. But let's think about a 2D XY model. Okay, so as I go around far from the core, my definition of a topological defect is going to be something that at every point along some circle or sphere or whatever far away from the core, the system locally looks like an ordered state. In other words, here the spin's pretty much constant, here it's pretty much constant, and so on, but which ordered state I'm in changes smoothly as I go around this giant circle. In other words, this giant circle is a map from, or as I go around the circle, I get a map from S1 in real space to the so-called order parameter manifold. which is the set of inequivalent ordered states. The way that people often formally define this is that this is cosets of any leftover symmetry at low temperature, called the residual symmetry, that group in whatever the symmetry is, the unbroken symmetry at high temperature. So if you want an example, in this XY model, there's no leftover symmetry. We've broken O2 down to, or SO2 down to nothing, so this is just SO2, which is, as a manifold, the circle. A ferromagnet, a uniaxial ferromagnet would be SO3 cosets of SO2, which will give me S2 for the uniaxial ferromagnet. So that's an example of this business. Okay, so that means defects, the different defects I can label by what is their homotopy class as I circle them. So that's saying, in the simple example, that pi1 of S1, we know that's Z, which means that the 2D XY model has vortices, but pi1 of S2 is trivial, which means there are no vortices in the 2D Heisenberg model. If we wanted to think about a three-dimensional problem, well, if I now think about 3D, then a line defect is what's enclosed by a circle. So pi1 tells me about point defects in 2D. It tells me about line defects in 3D. And therefore, logically, what is a point defect in 3D? A point defect in 3D would be something that's enclosed by a sphere, which means point defects in 3D are classified by pi2. A so-called hedgehog, I guess, is a defect of the uniaxial ferromagnet in 3D. So again, things are poorly defined at the core. If I had the vector pointing everywhere outward, the identity map on the sphere, that would be an example of a non-trivial topological defect of the Heisenberg model. And if you wanted to go one step further this way, you could and say that pi 0 is just the number of disconnected ground states. Okay. And then finally, the other thing you use these homotopy groups are things that are not quite defects, but topological structures. Skyrmion is maybe the best example. Okay. I think we have 4 minutes before the lunch person gets angry. So these are different from defects in that there's no core. As a simple case, if I took the plane, well, the plane, and let's say that all this, now I want to think about the Heisenberg model in the plane, and let's say that at infinity all the spins point up. Well, if I took R2 with the requirement that all the spins at infinity point in the same direction, then that's topologically S2. I know that there are non-trivial maps from S2 to S2 because pi2 of S2 is the integers. So that's like a Skyrmion configuration. It'd be something where as I go in, let's say the spin at the origin is down, and as I go from out here to in there, it's possible to smoothly fill this in, but in a topologically non-trivial way. So you can look online for a picture. I won't try to draw one. But so the Skyrmion is something where there's no point anywhere in this plane where there's any singularity. So if I want to go one step beyond point defects, then pi2 would be like I don't want to call them defects anymore. Let's call them topological structures. In 2D, like the skyrmion. So not a defect. And then the reason why people like Merman and Ponaru wrote these articles, if you're just dealing with S1 or S2, you can probably get by with your intuition and pictures. Once you talk about liquid crystals or cold atoms with spin, for example, the order parameter manifold can get quite complicated. For example, some of these manifolds that we think are physical actually have non-abelian vortices in the sense that the first homotopy group is not abelian. So for stuff like that, then you do need some of the mathematical machinery that's in these papers to compute homotopy. So as a closing example maybe to think about, we said that the Berry phase, if you want a problem that is more directly related to Chern number, let's say I went from T2 to non-degenerate two-band Hamiltonians. So this is kind of the ancestor of Chern number in the simplest case. So 2D would be the two-dimensional Brillouin zone. This would be something with a lower band and an upper band. Then what we've kind of claimed is that this, for this particular calculation, is close enough to S2. And here, well, this is, if I think about what are non-degenerate two-band Hamiltonians, that's basically R3 minus the origin. A two-band Hamiltonian is an additive constant plus coefficients of the three Pauli matrices. Non-degenerate just means they're not all zero at the same time. But just like the punctured plane was kind of like the circle, the punctured three-sphere is kind of like S2, topologically. You could imagine kind of pulling out from the origin and pulling in from infinity to collapse on the sphere. So that's why I think of the S2 to S2 map as really not very different from the somewhat more complicated thing that'll be the hero next time, which is the Chern number of two-dimensional problems. Okay. Any questions before we eat? Sorry if I ran us right to 12:30. Okay. Well, yeah, it's not really a substitute for a course. It's something that... Nakahara is kind of a physics maybe more
There were a few cases in which we really used to use about electrons, but of course, well, normally when you think of it, you fill means trivial.
That's right. But you only make it trivial by letting it be degenerate. If it's non-degenerate. Oh, I see. But it's non-degenerate. You mean representation. I think what you mean is maybe... okay.
If you go from the torus...
I guess I'd say there's an upper band and a lower band which have opposite Chern numbers. So if you mean the total bundle is trivial, that's right. But
You have to separate them.
That's right. Yeah,
Okay.
that's right. I would think about just the lower band, say, will give me one integer, and it turns out that the two integers have to add up to 0 because, as you said, the whole bundle is true.
Okay. Thank you very much.